Alright, this is our last video, rational functions and rational inequalities. I'm not going to do much with the rational inequalities. I'm strictly going to do the rational functions piece of this. So, definitions and useful notation, vertical asymptotes, horizontal and oblique asymptotes, graphing rational functions. We're stopping there. Okay, so a rational function is a form of a fraction. Rational usually means a fraction when we're talking about math. P, X, and Q of X are polynomial functions. Q of X is not equal to 0. That's the symbol there that has the funky little strange mark. That should be not equal to, because the denominator can't be 0. And so there are some values. If Q is factorable, there will be some values of X for which Q can be 0. And at that value, the function will be undefined. And so that's where your vertical asymptotes will be. And so the domain of the function, the whole function, will be all real numbers except anything that would make the denominator 0. Okay? So it might be everything but one number. And you'll see that as we do some examples. So let's go on. Vertical line, X equals C is a vertical asymptote. If f of X will increase or decrease without bound as X approaches C. Vertical asymptotes appear in figure 2. We'll see those. The graph will never cross a vertical asymptote. It will always just curve and go up or curve and go down at a vertical asymptote. So you can see, here's some examples. This vertical asymptote is at X equals 2. And the graph, in the first graph, they're both coming towards it and then increasing. The second graph, the middle graph, they're both coming towards it and decreasing. And in the last graph, the one on the left approaches it and goes down, and the one on the right approaches it and goes up. And so these are typical examples of how a rational function might graph. They're usually going to have vertical asymptotes. So let's look at, there's also horizontal asymptotes. There's 3 case scenarios for where your horizontal asymptotes will be. And what that do, where the horizontal asymptotes are, X will approach negative infinity or positive infinity. So they're going to level off and go sideways at the horizontal asymptotes. It can intersect a horizontal asymptote near the origin, but will eventually, from one side or the other, go out towards infinity. Okay? So here we have, looking at the first graph on the left, you see it goes to negative infinity on the top part of the graph. It goes to positive infinity on the bottom part of the graph that is below that horizontal asymptote. We do see it crossing the horizontal asymptote in one place in the middle graph. And then as it goes left and right, it goes to negative infinity and positive infinity. Then in the last graph, we go to negative infinity and positive infinity. And the middle graph looks like a cube root function, and it crosses right there basically at the origin. So you can cross a horizontal asymptote, usually in one place. But you never, ever, ever cross a vertical asymptote. Okay. Oblique asymptotes are slant asymptotes. They occur when the degree of the numerator is larger than the degree of the denominator. And what you'll do is you'll divide them with long division to find the equation of the slant asymptote. And the graph can intersect an oblique asymptote. So these look something like this. They're going to approach the asymptote and go to infinity or negative infinity, but occasionally they might cross. Okay? The graphing calculator will help you with these if you have one. Hopefully you do. So asymptote notation. This says X is approaching C from the left or the negative side. X in the middle there, it's the notation X approaches C from the positive side, and the notation X approaches C is used when describing behavior that's the same on both sides of the asymptote. So if we look at this asymptote notation here, this says the function approaches negative infinity as x approaches 2 from the negative side. So in other words, in this first graph, here I'm approaching 2 from the left, and it's going to turn and go to negative infinity. As x is approaching 2 from the positive side, it turns and approaches infinity. In this middle one, g of x approaches negative infinity as x approaches 2. So in other words, either way, from either side, when it approaches 2, it turns and goes to negative infinity. Here on the last one, h of x is approaching 2 as x approaches negative infinity. Okay, so the function is approaching 2 because my asymptote is at 2. The function is approaching 2 as x goes more towards negative infinity, and h of x, or the function, is approaching 2 as your x values are getting larger to positive infinity. So that's the way you would notate that it's approaching that horizontal asymptote. Okay. So equations for vertical asymptotes. Let's just go on and look at some. Find the domains in the equations for vertical asymptotes of the following functions. So the first thing you want to look for is what makes your denominator equal 0. That's really, it's as simple as that. So in other words, you're going to set your denominator equal 0, and you're going to solve it. So x equals negative 2. That's your vertical asymptote. Right there. You just solve for your vertical asymptote. Okay, what is the domain? Your domain is that x cannot be negative 2. It can be everything else but negative 2. Okay, so in other words, it can go from negative infinity, should be negative 2, to negative 2. It can't ever be negative 2. It's going to union negative 2 to infinity. In interval notation, that's how you would write that domain. Alright, what makes the g of x, what makes this second denominator equal 0? Well, we're going to try to factor that and see. Can we factor it? It will be x, there'll be a plus, and x and a minus, and 5 times 3 is 15, so positive 5 and negative 3 would add to be positive 2. So in other words, x can't be negative 5, and it can't be positive 3. That's your domain. Your vertical asymptotes are x equals negative 5, okay? So my vertical asymptotes are x equals negative 5 and x equals 3. Okay, now how do I write the domain? This is my domain, what it can't be. So I'm going to say negative infinity and to negative 5, union negative 5 to 3, union again 3 to infinity. Okay. Now looking at C, we need to factor. Nothing would cancel in A or B, but let's look at C. If we simplify this, we have x times x minus 1 and over x minus 1. So this factor cancels. So 1 makes my denominator equal 0. So x can't be 1, which is a domain then, is negative infinity to 1, union 1 to infinity. But since that factor canceled, that's not really an asymptote. That's going to be a hole in our graph. And so it's not actually an asymptote for this one. X equals 1. We would think might be an asymptote, but it's not. It's going to be a hole. And what you would do is you would put your value for your x back in here, So you'd have 1 squared minus 1 over 1 minus 1. I think it's going to be a whole, excuse me, at 1, 1, because the value of x is left there. Excuse me. But let's double check and see what. I believe you're going to have a whole at 1, 1. Okay, so let's look. Get out of this and go back to their solutions. Zeros from the denominator, so x equals -2, there's your domain. X equals -2 is your vertical asymptote. X not equal -2 is your domain. For B, we factored our denominator. -5 and 3 both make the denominator 0, so there's your domain, which we already did. And your vertical asymptotes are x equals -5 and x equals 3. Okay. The last one, the denominator's in factored form, so we can see its only 0 is at x equals 1. So there's your domain, which we figured out. And then we looked for common factors. And there's no vertical asymptotes because that factor cancels. And so it still has the domain of all real numbers except 1, but it has no denominator when it's reduced, so there's no vertical asymptotes. Okay. Now, horizontal and oblique asymptotes. In a horizontal asymptote, it's 3 different cases. You look at the degree of the numerator and the denominator, which is the highest power of x. If the numerator degree is less than the denominator degree, then it's always the y equals 0 or the x-axis is your horizontal asymptote. If the degrees are equal, you take the ratio of the lead coefficients. And we'll have some examples of that. If the numerator degree is only 1 bigger than the denominator, then it does have an oblique asymptote. But it has to be only, like, the numerator would be x cubed, the denominator would be x squared. Okay? If the numerator degree is greater than the denominator, and I may have said that wrong, I may have said the number 3 backwards. But if the numerator is greater than the denominator, then there is no horizontal asymptote at all. Okay, so let's look at some examples. We want to find the horizontal or oblique asymptotes for all of these A, B, C, and D. So let's look at the first one. They don't write the, okay, let's look. I wish they wrote it down. Okay, we look at A. We have x squared over x squared. The highest power of x is the same. So then you look at the numbers in front. So there's a 1. If there's nothing, it's understood there's a 1 and there's a 1. Okay, so in this case, the horizontal asymptote is going to be y equals 1. Remember, a horizontal asymptote is y equals, or an oblique is 2. So this is y equals 1. Okay. Now, here we have a 4 and a 6 for our degrees. So the numerator degree is less than the denominator degree, so it's going to be y equals 0. Okay. And on the B, we have a 3 and a 2. This is 1 larger. The numerator degree is 1 larger than the denominator. Okay, so this should have an oblique asymptote because it's only 1 bigger. This one is bigger, so it's going to have no horizontal asymptote. And really, neither does this one. This doesn't have a horizontal asymptote either. It has an oblique asymptote. So if the numerator degree is bigger than the denominator degree, there is no horizontal asymptote. If it's only bigger by 1, there's no horizontal asymptote, but there is an oblique asymptote. Okay, so let's go back and look at their solutions. And again, 1 is the horizontal asymptote, so that'll be y equals 1. the degree of the numerator is 1 more than the denominator, so we have an oblique. And what you're going to do is you're going to do polynomial long division. And so we've done that in the past, in a past unit. So you're going to divide x squared into x cubed and get x, and go through and do your long division. Okay? And you're going to end up with x plus 1, and there's probably going to be a remainder. You don't worry about the remainder for the oblique asymptote. It's just the quotient part that's your oblique asymptote. Okay? So again, you get x plus 1 plus some remainder, but we don't use that. You only use the x plus 1 part. So that's your oblique asymptote. And C, the degree of the numerator is 2 less than the degree of the denominator. So y equals 0 was horizontal. We already said that. And then D, there's neither, the degree of the numerator is 2 more than the denominator. So there were no horizontal or oblique asymptotes. Okay. Graphing rational functions. We're going to factor the denominator to determine any vertical asymptotes, cancel any common factors. Any common factors will be called holes in the graph, or vertical asymptotes. Then we're going to look at remaining factors to determine horizontal asymptotes, look at degrees of numerators and denominators, find horizontal or oblique asymptotes. Then we're going to pick some x's, find the y-intercept if we can. Remember, y-intercept, your x's will be 0. X-intercept, your y will be 0 if we can figure those out. And then we might just have to pick some x's and plot some points to find the trend, where it's turning up or turning down. So here we have a graph of x squared minus x over x minus 1, x squared plus 1, x squared plus 2x minus 15, and then x cubed. So I hope they'll do these one at a time and with some detail, but let's go on and just kind of look and see what their slides have. Okay, so we know on the first one, x is equal to 1, x can't be equal to 1. There's the equation. So my vertical asymptote is at x equals 1. We also know that we have a factor that cancels. Okay, so we're going to factor it, and we have the x minus 1 that cancels. So that tells me there's a hole in the graph. Okay, so because x can't be 1. So we're going to graph it as y equals x, basically. But there won't be, at 1, there won't be any kind of there won't be a value, so it doesn't go straight. It's not continuous. There's a hole there at 1, 1. Okay? In example 1b, we have this. We factored the denominator. These were all the ones we had before. So we found that we had vertical asymptotes at -5 and +3. And so we know that the graph has 3 parts. We look at the degrees of the numerator. We have an x squared over an x squared, so we know we have a horizontal asymptote at y equals 1. Okay? Because the ratio of the lead coefficients was your horizontal asymptote. So we're going to plot our asymptotes. There's our vertical asymptote and our horizontal asymptote. Now we have to look at, well, if we make x equals 0, what's y? Okay, so we're going to set x equals 0 and find that the y-intercept lies at 0 and -1/15. We can't solve that for 0, so we don't have any x-intercepts. And so we're just going to have to pick some points and plot them to get a shape of the graph. And so you might pick, there's our y-intercept. You might pick -1, -2, +1, +2 to see some trends in that middle part. You're going to have to go out and plot maybe x equals 5, plug it back in, x equals -6, 7, plug those back in to get some trends of what that graph looks like. And that's hard work, but with a graphing calculator, often you can go ahead and get some points just using the table of your graphing calculator. But if not, you need to make yourself a table. use your equation that you know. You're going to pick your x's. You might go to how -7, -6. You might pick a 5 and a 6. Any point, any x you pick, you plug in to that equation, and you see if it's where it's going to give you your y value. Okay. On C, the denominator of the function can't be factored, so the domain can be anything. And we also saw that this had an oblique asymptote of x plus 1. So we're going to, if we put our 0 in, we can see that we have 2/9 is our y-intercept. And x-intercept, we can do a couple different things. But we can also just calculate points and put in an x, figure out what the y is. We can factor the numerator. You may not want to go to that much trouble because it's an x cubed, and that's certainly up to you. But we do have a -1, 0 as our x-intercept. And so we can plot these points and see that we have a slant asymptote, and the graph itself kind of hugs that slant asymptote and goes up towards infinity and down towards negative infinity, and left and right towards infinity and negative infinity. Okay, we're not going to do the inequality piece. Graphing rational functions is a little bit difficult, but I hope you have good luck and can do it. If you have any questions with any of these, please call me. Don't hesitate. I will call you back or answer you back as soon as I can.